This is the final course video for the class Innovation in Science and Engineering, 18605 at Carnegie Mellon University. We are Team Franklin, and our team consists of Tenaya, John, Rahul, Zheng, and Skanda. Over the course of this video, we're going to highlight what the general problem presented to us was, how we chose and specified a particular problem, and how we solved it. This should cover all the S's mentioned in class, with this video being the final two S's, selling and success. First, the overarching problem, isolating a single dolphin's voice and speech from a tank filled with multiple speaking dolphins. We began by listing the constraints and problems the Disney team faced. Dolphins make two sets of sounds, burst pulsed clicks and whistles. These sets of sounds have different frequencies, some much higher than the human auditory range. As shown here, humans can hear between 31 Hz to 19 kHz, while a dolphin can hear between 150 Hz to 150 kHz. Further, dolphins can mimic each other's pitch and tone perfectly. While the reason for this is currently unknown, their mimicking nature can be shown in multiple facets of their personality.
This is a video taken from the Dolphin Research Center in the Florida Keys. Here we can see a blindfolded dolphin can mimic a fellow dolphin without sight. We assume they communicate through underwater whistles and clicks, still allowing mimicking actions. This is an example of their extensive ability to mimic not only each other's sounds, but actions.
Finally, recording audio data is hard, as we have to account for the noise of the tank, the water, the movement of the dolphins, etc. Next, we focused on what the Disney team already has. They have a main tank in which multiple dolphins can be held. They have solitary tanks for single dolphins. Also, both tanks are equipped with microphones to record data in the frequency that the dolphins speak in. So we began listing different ways we could narrow down the problem to a level that was more manageable for the scope of this project. In order to do this pictorially, we created a problem specification tree, which is shown here. We first established the root problem. We then listed all the potential areas of development. Systematically cancelling the options we felt infeasible, we proceeded to the problem we felt was best suited to this answer. The reasons for infeasibility generally fell into the following categories: too hard or nonsensical to implement, out of scope for the team's knowledge and experience, out of scope for the time and effort needed for this course. We then proceeded to state the problem in the most general terms so as to not pigeonhole ourselves into a solution. The statement turned out to be how to attach a sensor or sensor-type device to or around the dolphin such that it can detect when or what the dolphin is saying and potentially communicate this to the recording devices, either the scientists or the electronic recorders. The next step was to break down this problem into manageable parts. First, what kind of sensor? Either a light sensor, a motion sensor, audio sensor, vibration sensor? Next, where do we attach it? Externally with glue? Internally like a pacemaker? Maybe even suction cups? How should we transmit the signals? And how should the transmitted signals be received and stored? So what kind of sensor should we use? Well, this is the way the human vocal cords work. The vibration of the cords shown here leads to the vibration of air passing through them, resulting in the sound being produced. Dolphins have a similar structure by which phonic lips vibrate, creating noise, as shown here. The debate came down to choosing what vibration we needed to measure: the vibration of the air passing through, an audio sensor, or the movement of the dolphin tissue itself, a vibration sensor. Well, we decided that to observe the sound produced by the dolphin, it would be best to use a vibration and audio sensor so that we can notice the vibrational and audio changes. The vibration sensor would not be affected by external sounds but has the disadvantage of picking up stray movements. The audio sensor would be good for disregarding the stray movements but will be affected by external sounds. Hence, using a combination of the two would be best. Now, where do we attach it? What are we going to be sensing exactly? We decided to attach it to the dolphin we realized was the audio output station, namely the dolphin's melon, pointed to over here. After researching some underwater signal transmitters, we discovered that deep-sea divers use radio. From what we found, radio waves work well for our purposes, as one can distinguish which radio sends the signal by observing the frequency channel it uses. Hence, we decided to use radio signals. Finally, how is the transmission going to be received and stored? We decided to use the twin radio receiver of the radio transmitter to receive our specialized signal and the general microphones used by Disney to record the audio. Thus our finalized problem comes to be, how do we attach a combination of an audio and vibration sensor to a dolphin such that it recognizes the vibration of the dolphin hull and transmits to the receiver both the dolphin ID and sound in real time. The next level was coming up with technologies and ideas to create the solution. We first focused on finding a combination of a vibration and audio sensor. We decided to settle on the thromic sensor, a dual vibration and audio sensor meant to act as a microphone for the throat. After listing a variety of devices and conducting research on technology that may meet our needs, we settled on a modified version of the accessory XN-M915B thromic sensor. To hold sensor and other devices, we propose using the pre-made vests made by UNESCO, the Underwater Explorer Society. As we decided with underwater two-way radios, the natural product was to choose the Ocean Reef Used Underwater Two-Way Radio Communication Unit. Compiled, our final product will look like this. Highlighting the key areas, we see that the sensor will be placed over here. The transmitter is located here on the vest. The receiver, along with Disney's existing technologies, will be located along the edges of the tank. Right now, we have a design and the specs. The next step is to actually build the product. We expect the price breakdown to be: the XN-M915B thromic sensor costs $40. Multiple of them are needed. The Ocean Reef Used Underwater Two-Way Radio Communication Unit costs $449.95, and multiple units of them are needed. The Dolphin vest will be borrowed from UNEXSO conditionally. Multiple are needed. Potential audio editing software, Nuendo/Acid Pro, vary in costs. Further, extra costs for compilation will estimate to around $100. All in all, the total cost can be estimated to come to around $1,000 USD. What do we expect the final results to be? We're now going to run through an instance describing the working of the device. The thromic sensor senses the vibration and noise coming from the dolphin. This signal would be directly audible if we used a earphone. Instead, we will be transmitting it through a two-way radio. The two-way radio helps in transmitting different signals through different channels. Therefore, we can have multiple thromic signals which are channelized separately through the two-way radio. The receiver radio receives the signal and processes it into an audio form. The audio form can be processed through a computer which records the audio pattern. We can easily identify which dolphin is speaking due to the signal generated by the thromic sensor, combined with the knowledge of which channel the signal came from. With existing software that Disney has, or advanced music processing software like Nuendo or Acid Pro, the separate channels can be recorded as different tracks, and the different channels can be tagged with different dolphins. And that is our final proposal. Thank you very much for your time. Are there any questions or feedback?